Hi everyone. In this lecture, we will look at relational data. It is very rare that a data analysis involves a single table of data. Typically, you will have multiple tables and you have to combine all of them to answer the questions that you are interested in. And collectively, multiple tables of data are called relational data because it is the relations and not the individual data sets that are important. If you want to work with relational data, we need three families that are important. One is mutating joins. This allows us to add new variables to one data frame from matching observations in another. Then we have filtering joins, which filter observations from one data frame based on whether or not they match an observation in the other table. And finally, we have set operations, which treat the observations as if they were set elements. Now, the most common place to find relational data is in a relational database management system, what we also refer to as RDBMS. And this is a term that encompasses almost all modern databases. So if you have used a database before, most likely you have worked on SQL, which is structured query language. If you have done that, you should find the concepts in this particular chapter a little familiar, although the expression might be a little different. So let's take an example. We will look at library and tidyverse, and then we look at library and NYC flights 30. Right. So let's look at the airlines data first. We have a 16 by 2 table and we have the data like this, which is simply the first column, which is the information for that specific carrier, and then we have the carrier name as well. If you look at airports, airports gives us information on all the airports. So there are 1458 records. After this, we have planes, which gives us data for different types of planes. This is identified by the tail num. We have weather, which gives the weather at each NYC airport for each hour. So there are 26,115 records. One way to show the relationship between all these tables is in a drawing like this. Here we can see how the flights dataset is in the center and airports, planes, airlines, and weather is connected to this dataset. Now this diagram might seem a little overwhelming, but it is simple compared to some of the other things you will actually work on. The key to understanding diagrams like this is to remember each relation always concerns a pair of tables. That means it is connecting two tables. So you do not need to understand the entire thing, you just need to understand the chain of relations between the tables that you are interested in. For example, flights connects to planes via tailnum, flights connects to airlines via carrier, flights connects to airports via origin as well as destination. That's why there are two lines here. Flights connects to weather via origin, which is the location, and the year, month, day, and hour, which is the time. Let's come back. Now we want to look at the concept of keys. The variables that are used to connect each pair of tables are called a key. For example, when we connect tailnum and tailnum, this is called the key. This uniquely identifies an observation. For example, each plane is uniquely identified by its tail number. So there are two types of keys. We have the primary and the foreign key. The primary key uniquely identifies an observation in its own table. For example, tail num is a primary key, and tail num in the flights data is a foreign key. Now, in certain cases, a variable can be both a primary key and a foreign key. For example, origin is part of the weather primary key, and it is also a foreign key for the airports table. Okay, so once you identify the primary keys in the table, it is a good practice to verify that they do indeed uniquely identify each observation. One way to do this is to use count and look at the primary keys and look for entries where the n is greater than 1. So we will simply write planes, then we have a pipe, count tail num, filter is n greater than 1. And as you can see, we get a table with two variables. After this, if we are again doing weather, we can get a table with 3 into 6, right? Now, sometimes a table does not have an explicit primary key. So each row is an observation, but no combination of variables reliably identifies it. As an example, what is the primary key in the flights table? Let's look at that. So notice here that the date plus the flight or the tail number might look like the key here, but neither of those are unique, right? Because if you're looking at the date plus the flight or the tail number, there might be multiple occurrences. Let's look at it once again. If you look at the tail num, again, they're not unique. When you start to work with this data, we have assumed that each flight number would be only used once per day. And obviously, that would make it much easier to communicate problems with a specific flight. But unfortunately, that is not the case. So what do we do? If a table lacks a primary key, it can be useful to add one with another column, which is using mutate. And that will make it easier to match observations if we have done some filtering and want to check back with the original data. We usually refer to this as a surrogate. Alright, so a primary key and the corresponding foreign key in another table form a relation, and relations are typically one to many. For example, each flight has one plane, but each plane has many flights. In some cases, you might also see a one-to-one relationship. And there are also certain cases where there is a many-to-many relationship, even though that's fairly uncommon and that's a more advanced topic. So the first tool we will look at is mutating joins. So we've already done mutate earlier that allows us to combine variables, or rather combine variables from two tables. So it first matches observations by the keys and then copies across variables from one table to the other. And just like mutate, the join functions add variables to the right. So if we have a lot of variables already, the new variables will not get printed out. Let's see. So here we're looking at an object which is flights 2. We are selecting these columns and we get the result like this. There are 336, 766 more rows. If you remember, we can also write view, and that would allow me to view this data not in my console but as a separate tab like this, which makes it much easier, very similar to how you would view some data on Excel. If you want the full airline name to the flights to data, we can combine the airlines in the flights to data frame with the left join. So just like we use joins in Power Query on Excel or on SQL, we can do that here like this. So we get the name here. Now this creates an additional variable called name, And this is why we call this a mutating join. There's one other way of doing this, which would have been to use a base subsetting. Now this will look a little more complicated, but I hope this makes sense. We're simply using a base subsetting where airline's dollar name, right? And we're doing a match. So please make sure to practice both of them, even though the first one probably looks much simpler. Now let's understand how joins work. So I want to take a few examples here, everyone. Let me come back to my PowerPoint. Now this is one example where we have visual representation. The colored column represents the key variable, and these are used to match the rows between the tables. And the gray column represents the value column that is carried along. So a join is a way of connecting each row in X to 0, 1 or many rows in Y. And I want to show you one more diagram which will show the potential match as an intersection of a pair of lines like this. So this is how we are looking at the intersection. If you look very, very closely, you will notice that we have switched the order of the key and the values in X. And this is to emphasize that joins match based on the key and the value is just carried along for the right. That's why the value I've shown like this, and this is how we are joining it. So in an actual join, matches will be indicated with dots. The number of dots is the number of matches, which is also equal to the number of rows in the output, which will look like this. So if you notice 1, we get x1 and y1, 2, we get x2 and y2. And this is the simplest type of join, which is called an inner join, which means that it matches the pairs of observations wherever the keys are equal. That's the reason x3 and 3 and 4 are not picked up, because these are not matching with each other. And what is the output? The output is a new data frame that contains the key, the x values and the y values. All right, let's take an example. So I'm just going to first create my x and y. So let's go back to R and we will create two triples, x and y. And once we have done that, let us look at an inner join. As you can see, x1, y1, x2, y2. This is how we do an inner join. So the most important property of an inner join is that unmatched rows are not included in the result. This means that generally inner joins are usually not appropriate for use in analysis because you lose a lot of observations. It's very easy to lose them. After this, we come to the outer join. Now this one is a little more complicated than the inner join. So the outer join works a little differently. Let me give you an example. In outer, we will have left, right and full, which looks like this. So an inner join only keeps the observation that appears in both the tables, but an outer join keeps observations that appear in at least one of the tables. So left will keep all the observations in X, right will keep all the observations in Y, and a full join will keep all the observations in both the tables. That is why we're getting 1, 2, 3 and 4. Even though 3 and 4 are unique to the two tables. So these joins work by adding an additional virtual observation to each table. And this observation has a key that always matches if no other key matches, and your value is filled with NA. That's why you notice there are two NAs here. And this is how it graphically looks. Now the most common one is the left join, and we use this whenever we want to use a lookup to add additional data from another table, because it preserves the original observations even if there is not a match. Think of this like the VLOOKUP that we use on Excel. And like I said, most likely the left join should be the default join that you're using, unless you have a specific reason to use any other type of join. Another way to depict the different types of joins is with a Venn diagram like this. However, this is probably not a very good representation, but it will help you understand how the joins work. Now, so far, all the diagrams, we have assumed that the keys are unique, but that might not always be the case, right? So it is possible that one table has duplicate keys, and this is useful when you want to add in additional information, as there is typically a one-to-many relationship. Let's take an example. If you look at this visualization, you would notice that we have duplicate keys coming. So one is coming one time, but two is coming two times. So the table on the left has many and the table on the right has one. And the result will look like this. Let's take an example. So I want to do a left join, remember? Let's come back to R. And we will first create a triple, another triple. And when I do a left join, get the result like this. So x1, x2, x3, x4, y1, y2, y2, y1. The other possibility is that both the tables have duplicate keys. Now this is usually an error because in neither table do the keys uniquely identify an observation. So when you join duplicated keys, you get all the possible combinations. This is also called the Cartesian product, and I'll just tell you what that is. Let's first look at the visualization. It looks like this. So if you notice, on the left we have 1, 2, 2, 3. On the right we have 1, 2, 2, 3. It doesn't really make sense because 2 is repeated in both the tables. And this is what we call the Cartesian product, which is nothing but, if I show you my browser, we have the Cartesian product. You can read about it in more detail if you want to. It's a simple set where you are basically saying that there are two sets which are denoted at A multiplied by B, and this is the set of all the ordered pairs where A is in A and B is in B. You can read about it. The Wikipedia article explains this very well. Let's take an example. Very similar to the previous one, we are creating this. So if you notice, we have 1, 2 to 3, 1, 2 to 3, x1 to x4 and y1 to y4, and the result comes like this. There are cases where this is handy, but this is not very commonly used. So far, the pairs of tables have always been joined by a single variable, and that variable has the same name in both the tables. And that constraint was encoded by the equal to key. Now we can also use other values for the by to connect the tables in other ways. Like here we were using this, which is the by equal to key, but we can also use something else. So the default is by equal to null, which uses all the variables that appear in both the tables. And this is called a natural join. For example, the flights and the weather tables match on their common variables, which is year, month, day, hour, and origin. Let's take an example. We have flights too. We are doing a left join on weather, and the result comes like this. Character vector, which is by is equal to x, is like a natural join, but it uses only some of the common variables. For examples, flights and planes have the year variables, but they mean different things. So we only want to join by the tail number, like this. We're only joining by the tail num this time. So note that the year variable, which appears in both the input data frames but are not constrained to be equal, are disambiguated in the output with a suffix. We can also do a named character vector, which is using a concatenate. Let's take an example like this. Here we see that we're using destination is equal to FAA, and this will match the variable destination in my table to the variable FAA in table Y, and the variable from X will be used in the output. So in this case, we want to draw a map where we need to combine the flight's data with the airport's data, which contain the location, which is the latitude and the longitude of each airport. Each flight has an origin and each destination airport, so we need to specify which one we want to join to, which is what we have done. This is my origin. All right. Now let's look at filtering joins. We've done mutating. Let's look at filtering joins. So filtering joins match observations in the same way as mutating joins, but they affect the observations and not the variables. So there are two different types here. We have a semi-join and we have an anti-join. So the semi-join will keep all the observations in X that have a match in Y, and the anti-join will drop all the observations in X that have a match in Y. And semi-joins are not very commonly used, but they can be useful when you want to match a filtered summary table back to the original rows. For example, imagine you have found the top 10 most popular destinations. So we can do this. So my top destination is the count head 10, like this. So we want to see the top 10. And now we want to find each flight that went to one of those destinations. So we can construct a filter by ourselves if we want to, which would be like this. We're doing flights, we're saying destination, and we're using in top destination. The field is destination. But this can be difficult to approach because if you want to extend this to other multiple variables, it is not that easy. For example, imagine that you found the 10 days with the highest average delays. But then how would you construct the filter statement that used year, month, and day to match it back to flights? Instead, we use what we call a semi-join, which connects the two tables like a mutating join. Instead of adding new columns, it only keeps the rows in X that have a match in Y. And this is how the result looks now. Let me also show you graphically how this looks. So graphically, the semi-join looks like this. And only the existence of a match is important, so it does not matter which observation is matched. That means that the filtering join will never duplicate rows like mutating joins do. The inverse would be a anti-join. So in the anti-join, we keep the rows that do not have a match, which means if you look at this result, everyone, we have our anti-join here. The result is only 3 because 3 does not have a match. So anti-joins are very useful for diagnosing join mismatches. For example, when connecting flights and planes, you might be interested to know that there are many flights that don't have a match in planes. Let's take an example. Like this. All right, so the data that we have been working with in this chapter has been cleaned, so we will have lesser problems than earlier. And do realize that when you work on your own data, it is unlikely to be like this. You have to get very comfortable with joins. Excellent. In the next chapter, we will look at how to work with strings